Hello, this is just a video that we intend to have a revision with the previous lectures we did hitherto, and we will keep going with the Friedmann equations and the accelerating gravitational field for the non-relativistic matter. In this video, let's take a look into the previous cases that we investigated. Triumphantly, we have reached and also we presented the Hubble constant, right? I mean, by the separation of the galaxies as angles, or maybe the distance, and because of the process, the distance between two galaxies were increased because of the expansion of the universe. And for the later videos, I mean, in the future videos, you can easily be able to understand and compare the consequences that the predicted calculations for the expansion of the universe is not consistent with what we observed in the 1998. So in the 1998, the astronomers observed Type 1a supernovae that it was an evidence that the universe was not slowing down. Instead of slowing down, it was accelerating faster and faster. And this expansion is actually exponential. So hitherto to the 1998, the calculations, the theoretical models and suggestions into this behavior of the universe were focused and also based on the gravitation. So the presence of the gravitational material in the space, then the consequences must be everything gets slowing down and getting closer. I mean, because of the presence of the gravitational forces, everything in the universe must pull each other. So the expected value, or the phenomenon, let's call it, was actually universe to slow down. But actually, after the observation, there were some inconsistencies in the calculations and with the observation that they observed from the hydrogen lines and the other variables in the supernovae 1a. So the predictions were not true, and we observed that it must be some other contribution towards the expansion of the universe, and it was actually the dark energy, the dark matter itself, which corresponds the vacuum energy itself has no zero energy. Okay, it wants to be in the smallest value of energy, but it doesn't mean that it is zero. So it was actually the reason why everything quarreled each other, and there were fluctuations about that. Yeah, for now, today's lecture, actually we will keep going with the Friedmann equations, second order, and the first order of Friedmann equations, so as to understand the expansion, and we will be able to understand the other contributions and how we add, such as the contributions of the dark matter itself. Okay, so for the dark matter, actually I intend to use the dark energy and its energy density, by the way. Just I will use some place in here. For example, let's rho stands for the energy density of the dark matter, and actually we call it rho vacua, the vacuum energy density. Let's call it vac, is equals actually rho c squared, this is the speed of light, and also c to the fourth divided by 8 pi g. So lambda here is the cosmological constant. So actually it must be U, the energy density. So energy density per unit volume or area, it doesn't matter what you call. It is actually that. So at the end, for example, we can be able to understand the Friedmann equations like that: a dot over a squared, some rest value of the Hubble constant divided by some variable that it call the x to the fourth. So there are contributions, and for example, rho omega matter plus So we, at the earlier cases, we actually demonstrated that the density of the material with non-relativistic matter is decreasing like 1 to the a to the 4th, sorry, a to the 3rd. That is the reason why, for example, you will write down here x, and for example, omega radiation, that's R stands for radiation, so it's about the, decreasing by a factor of x to the 4th, and by the way, let's call rho k. K is the curvature, actually, okay? So the curvature itself expanding like kc squared divided by a to the as a squared, so it must be x squared, e, etc. Okay? Are we recording that place, by the way? Yeah, okay, we are. Those are just the consequences we intend to reach. I will explain every equation in that place. All right. For the other previous cases, I demonstrated assiduously. I demonstrated the equations for the Gauss law of the gravitational field, which corresponds that we just investigated, or maybe like improvisation, right? There was a shell, and the shell that filled with the massive object. It doesn't matter the massive or the small masses they are. The importance is the presence of the mass in that shell. So the presence of the mass produces a potential distribution around the shell. That is the reason why any test particle, when they are in this field or when they are occur into this field, they exert a force on them. So it accelerates, right, towards the center of the mass, or maybe if it has the components of velocity, then it rotates around this center of mass, where the whole mass is embedded each other in the one point. This is what we call the stationary gravitational field. So the equations that we demonstrated in these cases were about the stationary gravitational area, the field, which is conservative. But we know today the universe is expanding, so the gravitational fields are also expanding, which means the shell is growing up. The radius of the shell is increasing as the time itself elapses. That is the problem. So if there is no non-stationary, if there is no stationary field, then it is not conservative anymore. That's the reason why, actually, right? For example, E field, right? If the charge is motionless, then the E field that it creates around it is conservative. So you can imagine this force can be also described as negative gradient of any scalar function, which is actually the potential energy of electric field. Same as the gravitational field. There's a mass which is not moving in this shell, or maybe it doesn't matter the point, the space. It means that the potential distribution of gravitational field is constant, stable. But if the particle moves, which means the mass moves, then it's going to be interchangeable and variable, by the way. Same as the electric field. If the field of electric field is not stationary, then it corresponds to the magnetic field. Magnetic field is just a method, right? We just use it so as to understand the interactions between the moving particles, and they reflect each other. The moving charged particles. Importance is that, okay? So I'm just cleaning the board right now and write down the equations for the accelerating gravitational field, whereby the first thing that we will investigate is the galaxy cluster, okay? Actually, we did it, I presume. Alright. I hate these people. Alright, just clean the board, the whiteboard, which is homemade, which is cheap. For the people who is frugal about that, yeah. I mean, it makes sense, right? Alright. Okay, in the presentation 4 and chapter 5, and by the way, the 4th, chapters, the presentation video, which is the 4th, I mentioned the enclosed mass, and by the way, its field, right? So, if you have some questions about it, I mean some not completed issues, then you have to take a look, because I will not derive these equations again. The Gauss law of gravitational field were presented in those videos in the previous cases, and same as the cosmological Hubble constant. We will not keep going directly with those equations. Okay, well, I can start off from here, and yeah, well, there's my pencil. Yeah. Now we can derive the equation again, but this equation is not stationary. So the first, it was the Laplace, right, of any scalar function. We call this phi is the gravitational potential energy. So this is minus 4 pi g m enclosed. Mass enclosed in that sphere. Doesn't matter numbers of mass. There are methods to solve it. There are methods to measure how much mass enclosed in that sphere or the chosen area, which chosen by you, by the way. So all of these topics were investigated diligently. I mean, we did diligency investigations towards the methods to find out how much mass that it enclosed in the previous cases, okay? Assiduously, we did it. So there's no problem then. Okay, so also I call this rho as a density of mass, so it can be written as 4 pi g rho, okay? So this is what we'll find out. This is actually Laplace, okay? And if this equation, the right-hand side equals 0, which means this is the harmonic function, okay? Which corresponds to the stationary case. But instead of this, we need non-stationary case. All right. So, for the given proper time, actually, let's call it time of initial picture, Ti, T sub I, whereby Ti is the time of initial picture, and rho I is also the initial density of mass in the first time you are observing, okay? So the expansion also can be written as a Hubble parameters, right? Vi, or maybe let's call it Hi times R, where Hi is here, A dot over A. Just take a look into the previous videos if you are confused about this differential form and what it is meaning and how we reached this equation. Okay, it's important. It's actually h of t is a Hubble constant. Okay, and this is actually initial distance between them. All right. So the mass that is enclosed in the sphere is actually can be shown as like, for example, here is the sphere, the galaxy cluster or the Gauss surface that I want to investigate. So it includes mass m, the whole mass inside of it, which is the function of r, right? Because of the radius of this thing, the sphere. So it's about m, let it call m re I, the first mass. So the density of mass in this given region is rho I equals mi divided by vi. Vi is this first volume of this sphere. So vi, what we can write down for the vi is actually rho e times v sub I equals mi, right? So vi is for divided by 3 pi rho I cube and times rho I equals the mass it includes on the first time of my observation towards the system. So the whole mass, if you can imagine, is embedded in the sphere, distributed homogeneously. Okay, homogeneity is done. Isotropy is done, which means that every observer measures every distribution same. In all directions, distribution of mass is same everywhere, no difference. And it is independent from where the observers are located, okay? So the distribution of mass in that given shell can be written as this, because it is homogeneity. So if there's a test particle in this field, the gravitational field, then it will exert a force on it, which might cause the motion. Or maybe it doesn't matter, but the orbit, the trajectory must be affected by the presence of this embedded mass in the field, in the shell, in the sphere, right? So to say, what we call the acceleration of this object, let's call r double dot. Dot is the time derivation, first and second time derivation, respect to the process, can be written as, for example, if it is the gravitation, let's call it g, minus gm is actually this one, the whole mass, right? Let's call it m rho I, divided by r squared, right? We will see that it will be the time dependent, but just I am showing. So for the m rho I, we can write down this. So minus 4 pi g divided by 3 rho I cubed divided by r squared is the acceleration of this test particle in the field, or maybe outside the field, doesn't matter. If it is in the field, then you have to find out how much mass enclosed in this other Gauss surface with different radius, which the radius, let's call it r1, is smaller than the max radius of this sphere. Let's call it r to the 0, the rest and the wall. So as you can see, the radius here is smaller than the radius here, right? So you need to find out how much mass that is enclosed in this the other shell that you choose, so as to understand the mass that is enclosed. And when you find out the mass, then you can find out the acceleration in the shell. If the wall, if the source is not absent, okay? If there is no absence, if there is no mass in the shell, then there is no gravitational force, such as the electric field in the conductive shells. Inside of the shell, there is no field because there is no charge density. The Maxwell's equation says that, divergence of the electric field is 0 if there is no density of charged particles. Okay, are we recording, by the way? Oh yeah, all right, very well. So this is just a force, and recollect, if r squared is equal to the first initial radius, then it's going to be that one. Well, by the way, I forgot to write the rho I, so as to write down this equation. Okay, now we know that the because of the expansion of the universe, everything gets further, right? The distances are growing up as the time passes. So this r must be the function of both r sub I and t. Why? Because the distances are what you measure. And the process, when, for example, t equals 0, you start observation. And meanwhile, after some process, you are just investigating the case again and take a look into the near distances about the nearby galaxies which you're surrounded by, and just you observe that the distances are not same as the distance you were observed in the first time, which is initial time, because of the expansion, actually. So in the 1998 observation, it was predicted that the universe is slowing down, but unless they observed that it was accelerating. So for example, just take a look into here. The minus sign here is also corresponding that it is gravitation. So as you can see, the distance where the r hat unit vector is directed towards the galaxy, or maybe the point that I want to understand, that I want to choose from me, right? I mean outside, outer. So the minus sign means towards you. Opposite direction of the r hat vector, the position vector, which corresponds that the gravitation in the dominance of gravitation, everything pulls together, opposed to the expansion. So the gravitation and the gravitational effects slowing down the expansion of the universe. This is what the theory expected hitherto 1998 and now. But what we observed is it's not important, because this is non-relativistic matter. For the other cases, not the case. We will write down the Friedmann equations like r double dot equals minus 4 pi g divided by 3. Here is the rho, okay, but the rho is the sum of the all contributions in the universe, such as, for example, rho radiation. Let's R stands for the radiation. Then rho matter, non-relativistic mass, and plus the curvature effects. The structure or the shape of the space also corresponds and also takes a role into the inflation of the universe. If, for example, the curvatures are not flat, then it's going to be, for example, the flat case is not occurring, so K, let's stand K for the curvature. If it is smaller or less than the 0, then yes, the universe is closed. Or maybe the K is bigger than 0, greater than 0, and then it's going to be the open universe, which affects the expansion, the Hubble constant. So here, rho K, and by the way, rho vacua, the dark energy, those contributions will affect the expansion. In the next chapters, which is so later, we will see that P divided by C squared, and also 2 rho here, for example. Those are just the pressure of the vacua in space-time tissue. So it cannot be written as directly in here, okay? For us, let us stay down in here. So this is just what I measure. So I can write down it as, okay. So we can actually, yeah, it doesn't matter actually. So Ray double dot I is the other equation actually, but there's no need to give it. There's no need to give it. You can easily say that if, is it visible, this place? No, not visible. Okay, I'm going to keep going from here. If r squared raised by t equals r initial q, r initial actually, not the components, then it must be vanished, right? So r double dot equals minus 4 pi g divided by 3 rho e divided by not divided times r Re e of t. And yeah, we can take a look into this one more time. Actually, this is the second order of Friedmann equation. If they are not equal, the functions are different. which means that the non-stationary case, by the way, it can be seen from here. If they are not equal, then the distances that you measured on the first time and second time are not equal. So there is difference in the ratios. So they differ each other. They are not equal. But if they are equal, then what you measure is the same expansion. So as you can see, the shell is increasing by a factor of r in these equations right now. Yeah, I'm not going to derive this equation actually, but we can keep going one more time so as to understand how rapidly the mass density affected by the expansion of this shell. So we can write down as, let's clean here. It's not that hard actually. You can derive these equations very well. And also you can write down like a double dot. A is the scale factor. You can find it from here, by the way. So for example, a double dot here is here, that's why. Is also the acceleration, right? For example, the first distance in the previous cases, a of t times some initial distance. So the first time derivative of it is the ratio how rapidly that they go away each other is a dot r sub I, and the one more derivative is the acceleration actually, a double dot times r sub I. So we can also write down the same thing here. It is a double dot. Let's call acceleration alpha because the symbols are same. Alpha double dot divided by a double dot equals r initial. So we can do the same thing again. That alpha double dot can be written as in the functions of that, respectively solved by this. Yeah, some copy. Okay, for the mass density, we know that rho. So this must be not initial, right? Because there's a process which started from the first observation we are doing. So it must be the function of time that varies with time. By the way, so this is about m I divided by v and v of I, v sub I. So it's making more harder. Yeah, I actually write down the same thing. This is initial volume, but this one is not initial, so we can write down it as, for example, what we found it here for mi. Mi is that one, okay? So I can write down this rho sub I 4 pi r sub I cube divided by 3 and divided by the initial volume, which we can call 4 pi divided by 3 and alright, let me say one more thing. Actually, I am just taking a look into the calculations I am doing every time. Yeah. Okay. R e cube. And here is one more thing, a cube t. As you can imagine, this a cube came from the scale factor actually. So the volume increased by a factor of a cube t. Is the new volume, right? Because these are just dimensionless numbers. For example, here is the first volume that at t equals 0 you observe this. You measure the volume of this shell, the gravitational shell which filled with the massive objects, the galaxies. And as some process occurs, as the time itself elapses expeditiously, then you will measure the other volume, which is the next volume actually, like this. because of the expansion, the volume increased, which means the radiation, not the radiation, the radius of the sphere, the gravitational field actually is increased. So the surface is increased, right? Because it was the Gaussian surface. So this surface was increased by a factor of A of t, which corresponds to the scale factor. So, for example, new distance, for example, the first initial distance is r sub I. Okay, so the corresponding volume is, let's call it V sub I. No problem. But after some time, after the expansion of the universe, meanwhile, the whole process will cause and lead us to write down this volume again, but by a factor of A of t. So this will be the new distance between the first volume and second volume. There are time separation, the time difference. So for the volume, we are just taking the cube, so it must be like this. There's no problem, right? Unless, instead of writing the new term, which is r cubed, I'm just writing the left-hand side in this equation. So this is actually the new distance. So this one is there, they are equal. But I'm just writing down as a functions of r sub I, because they will vanish each other, they will cancel each other. So I can see the ratio of how the mass density of the universe decreases as the time elapses, but it is for the non-relativistic matter. Here they are also going. So this is rho initial divided by a cube of t. Okay? So the whole process, rho t, which is a function of time, rho I divided by a cube of t. Rho I is the initial density of the sphere. Okay. It can be written as that. Alright. It's done. It's very well done. Maybe one more thing I can write as if I multiply in this equation, maybe it's not visible easily, but I can write down this, by the way. I intend to write this second order Friedmann equation respectfully to the ratio of the mass density. I mean, in the terms of mass density. So if I multiply and divide the both right-hand side into the r sub I, then a double dot equals minus 4 pi g divided by 3 rho initial divided by, actually this equation, what we are talking about right now, r cube of t here, and they will vanish. So, well, I think there's some problem, I presume. Let me say, am I wrong? Okay. Multiply by a double dot and a. U double dot is that one, surely, yeah, that I found. A double dot 4 pi g rho t a, and rho t is that one. All right. Okay, rho e times that. A double dot 4 pi g rho e. A squared is that one. So this is r squared. That's the truth one. So I multiplied both sides by r. So it equals here, actually, as you can see, here is what? Rho I divided by r cube. So minus 4 pi g divided by 3 rho of t times r. Actually, r here is the scale factor. Just the notation is different. Rotation is different. So we can write down the same thing again as that one. So A double dot minus 4 pi g divided by 3 rho I divided by a cube of t, and also a of t. A of t is also r. Just like switch the symbols, equals 4 pi g divided by 3 rho of t and a of t. This is the second order of Friedmann equations, if you want to say. Here is the density of the universe, and the expansion is by a factor, by the way, is like that. So this is a differential equation. A double dot plus 4 pi g divided by 3 rho t a of t equals 0 is our differential equation. If just an assumption, rho of t is a constant, then it's going to be exponential. I mean, the solution can be written as a to the plus or minus I omega t, or something like a h t, some constants. So is a cosinus or sinus, doesn't matter. Okay, maybe we can do this, by the way. So the other is actually, I will derive this equation, the first time derivation, which is coming from the total energy of the particle rotating around this object, and actually the object is the sphere of the gravitational field. Alright, in the previous video we diligently demonstrated the second order Friedmann equation, but for today's universe, with the other very types of contributions towards the expansion, it cannot be written as we did. So the general form is this is not today's topic. I mean, it is further, but I would like to write because it is more stupendous, and by the way, it has some fallacious misunderstandings, and by the way, fallacious assumptions, but in fact, all of them, when they are getting together, they are meaningful, trust me. So let's write down the second order Friedmann equation again, and which is about the gravitational effect of negative pressure, which is corresponding to the dark energy. We can write a double dot as a function of time, and which was a scale factor, minus 4 pi g divided by 3 is the constant number, right? You know how we get those equations again. Here is rho of n is also standing for the other contributions, such as the matter density, radiation density, fermions, bosons, and maybe electron and positron pairs, doesn't matter. Plus 3, I think it's going to be 3pn divided by c squared minus 2 rho vac. And also here can be written as the rho radiation and rho matter, as we said before. So P vac is actually the pressure of the vacua in the space-time tissue. So it's also can be written as, I'm just writing down the equations that I wrote earlier times. P equals Pn divided by, plus P vac. And same as the rho vac is, actually the rho is rho vac plus rho n, rho of n. Those are just the equations. For the other case, whereby actually this is second order, we assume that after 1998, the observations predicted that the vacuum energy density of the universe in the theoretical models must be stable. But for today's cases, we know that it has some fluctuations which are dependent into the string theory and the field theories. So it depends the entropy density and also the entropy of the homogeneity and the the vacua and the vacuum energy itself has also fluctuations inside of it. So the distribution becomes different. So we are using W-mapped methods to solve these problems. And for now, if for example, material density of the universe, which is non-relativistic matter, rho m, let's rho t equals, what was that? Rho m divided by a cube, right? But in fact, it is not. This actually assumes that the density of the material, which is mass, is stable. So if it is interchangeable respectively to the time, then the first time derivative must be minus 3 rho m divided by a to the fourth, right? Okay, in the previous cases, we diligently investigated and also demonstrated the expansion of the universe by using the second order Friedmann equations. But for those Friedmann equations which we demonstrated, they are not including the pressure terms. For now, today's cosmology, we are using the pressure effects, such as the negative pressure effect of gravitation, which is the repulsive gravity. So it depends the vacua and the vacuum energy density, and it corresponds that repulsive gravity fasters the expansion of the universe, unless instead of making it slowing down. Until the time 1998's observation, the theories predicted that the universe was about to slowing down because of the presence of the gravitation, not presence but domination. But what they observed, the astronomers on that very time, that they observed that from the type 1a supernovae, the expansion is inevitable and going faster and faster as the time itself elapses expeditiously. So actually here is the general term of the Friedmann equations, where rho n stands for the pressure and rho vac is the vacuum energy density, vacuum density of the universe, and rho n is the ordinary matter, such as mass, radiation. So it can be added such as rho matter divided by h to the third, and rho radiation divided by h to the fourth, right? Doesn't matter. Important term is here, because as you can see, it is very important. The negative sign corresponds to the gravitation, as ordinary gravitation, the Newton's gravitation. But just imagine if we multiply this equation with respectfully all of terms, it becomes positive. So the net sign of this term is actually positive, which corresponds that the vacua is increasing the inflation. It's not slowing down the expansion of the universe, such as the gravitation. So this term is actually what we call the repulsive gravity. And as you can see, 8 pi g rho vac. If rho vac is dominated, then h of t is the Hubble constant, right? A dot divided by A must be 8 pi g divided by 3 rho vac, if the vacua energy density is dominated. And for today's universe, it is. Unless there were some secret terms in this term, which they are not dominant, right? Actually, I can write it as that one, and actually, by the way, the root, right? And for example, rho matter, rho radiation, and the other contributions, and rho vacua. If it is dominated, they are negligible. So it makes the expansion faster. From the first order Friedmann equation, we dare to say that, what was that? H square of t equals a dot over a square, And also it equals 8 pi g divided by 3 minus kc squared divided by a squared, right? This term k depends the curvature, okay, but the curvature depends also the vacuum energy density. We will derive these equations, all of them, how the curvature or the shape of the space, the structure of the space is dependent into the vacuum energy density of the universe. So those are just the equations I wanted to say. So if rho vac goes to infinity, then h is about exponential. So h in the domination of the vacuum energy density goes to the a to the h of t, some constant times t, and it's going to be so fast, so big the expansion is. Actually, here the h, where is that? Here, h becomes the Hubble constant of vacuum energy dominated universe. So let it write down as h vac, vacua and the t. H vac is very big value, enormous, and the t, it corresponds to the process. Just imagine how fast the expansion is, how rapidly it occurs is. Okay, so it was just a demonstration for that time. I just wanted to say one more thing, that the pressure of the dark energy is also can be written as P vac, let's say, minus rho vac. Rho is the density of vacuum times c squared, and also it equals the cosmological constant times c to the fourth divided by 8 pi g. So rho vac can be written as in the terms of cosmological constant and 8 pi g is just a constant, not important. In general relativity, we assume that c is 1, just for the sake of the numbers and dimensionless symbols. Just it becomes easier to demonstrate. It doesn't change anything actually. You can add. For example, gamma is the Lorentzian transformation factor, y minus v squared, but it doesn't matter for the dimensions. You can write down c squared. It doesn't matter. It doesn't change anything. All right. Those are just what I wanted to mention for now. For the other first order, let me write down the first order Friedmann equation. And by the way, using this, you can find out the critical density of the universe, which is independent of time. And our assumptions in this video will be the dark energy density in the universe is stable. So the distribution is same everywhere. You will measure all the things which are same. All right. Let me write down that place in here. It is, I mean, it glimmers, right? Glimmer. So I'll say. So the first order Friedmann equation, and just imagine if vacuum is not occurring. I mean, if in your calculations, if the vacuum energy is negligible, then these two terms vanish each other, and just rho n is important, which is the non-relativistic matter and radiation energy density. The other Friedmann equation, which is the first order, a dot over a squared is h squared, and it is 8 pi g divided by 3 minus kc squared divided by a to the fourth. So if you solve this differential equation, doesn't matter. For example, if k is 0, is a... I am sorry, I talked that it was recording, but it wasn't. I don't know why it stopped the record, but okay, doesn't matter. Just 1 minute afterwards, I noticed that it wasn't recording. So let me repeat it again. If k is 0, then this term is negligible. So the differential equation is easy, which corresponds something like the exponential solution, right? Some constant, and this constant is actually this one, times t. as the process increases, as the time increases, then the expansion rate is increasing. Then these things are growing up. If this term is not negligible, it depends the sign of this thing. I don't like this country. Incorrigible people everywhere. Then why I am ferocious? Okay. Where was I? Okay. If the term is not negligible, then the sign of this term depends the ratio. For example, if k is the positive, which corresponds to the open universe, the shape, the size, then it will slow down the expansion, right? The negative contribution into the expansion, the opposed contribution. If instead of this, for example, this is positive, and if this term is greater than that one, then of course it will slowing down the expansion of the universe, as can be seen here. C is that one, so if it is dominated, then it will slow down. Just imagine from the x and y axis, the graphic parabol. Actually not parabol, like the exponential, decreasing. All right, so let me continue with the first order Friedmann equation. We will write down that one. All right, yeah. And by the way, we assume that the material density, non-relativistic matter, and the radiation are stable. If they are not stable, and for today's universe they are not, rho m, let's call it rho mt equals rho initial sum in, let's call rho m at 0 rest divided by a to the third, right? And if I take the first time derivative of it, it becomes rho m dot equals minus 3 rho m 0 divided by a to the fourth as a function of t and a of t. Sorry, a dot of t. I can write down as minus 3 rho m 0 divided by a cube of t times a dot over a. Is it possible, right? Yeah. Just math. Not a math, actually. All right. So here is, as can be seen, rho of t. This one, rho mt. And a dot over a, from the previous cases, we can write it as the Hubble constant, right? H of t. So, where's my ruler? I can write the whole thing again. Oh. All right. Rho dot m of t equals minus 3 h of t rho mt. If you solve this equation, this is also a differential equation, then you will also reach how rapidly the non-relativistic matter and their densities are slowing down or maybe changing. Same as radiation. Radiation mass, rho radiation, T equals rho R sub 0 divided by a to the fourth. So the one more time derivative becomes minus 4 h of t r rho R t. This is just a changing of this equation. Just imagine the gravitational effects which caused by the presence of the mass is also changing because of the presence of the negative pressure on the space-time. So this term, which means the density of vacuum energy, is also varying with time. So all contributions will be changed. They will determine the expansion of the universe. We will mention all of them in the next chapters, not now. Actually, I have completed one more course from the MIT and the Standford University, and I'm just giving a revision, by the way, as I am recording this video. Yeah. All right. Now from the first order Friedmann equation, we say that the particle has the kinetical energy and, by the way, the potential energy as it rotates around this sphere. sphere is the galaxy cluster. It's a Gaussian surface, right? All right. So one of them is 1 over A m. Let's call D or okay. A dot is a function of time, by the way, and R initial, the first coordinate, this stage, square, right? This is velocity. If you are confused from this notation, just take a look into the previous videos. Presentation 4 and 5, and also the olders, because it was that dt is the distance between two galaxies times equals some process, some scale factor times the first initial distance. This is the new distance after some process. So the first time derivative is that one, and second time, okay, you can write it. So we call it V. So 1 over 2 half mv squared is the kinetic energy, but instead of writing V, I wrote down in the differential form. So it is A dot times T, RR. R is not important. You will see it will vanish. It will cancel each other. So you can take it as one, doesn't matter what it is. And also the gravitational potential energy, G m divided by this one, A of T times RE, equals total energy, let's call it A. If A is 0, which means the critical solution. If A is a negative, then the test particle that is rotating around this galaxy cluster will be pulled towards the center. So the orbit, the radius of this test particle's orbit will be decreased as the time elapses. It has components of velocity, okay, so it will rotate by a factor like this, but the radius will get smaller. If A is positive, the kinetic energy is dominant, which means that the test particle can escape from this gravitational field, but still in the circular orbit, because there are components of velocity which is being affected by the gravitational pulling from the enclosed mass in this cluster. Cluster is just a name of astronomical or astrophysical frame of observation. Gauss surface or the sphere is just the frame of physics. Okay? Demonstration. So, if I multiply both sides by A of T squared, and let RE stands be 1, okay, just imagination, it doesn't matter. Units are not important. Those R sub i's will be vanish, cancel each other. No importance, no contributions, trust me. 1 over 2 m A dot of T divided by AT squared minus G m divided by A cube of T equals A divided by A squared of T. And one more thing I can do is to divide this equation by the small m, which is the test particle's mass. So they are going, and it becomes here, right? No problem. And one more thing, that I can multiply both sides by 2, and here it vanish. Here becomes 2, here becomes 2. In this case, for example, in the previous minutes, I write it minus kc squared divided by a squared. Is same as that one, okay? Just notation is different. We will use it in actually metric, Robertson-Walker metric. K is the some angle. For example, minus c squared dt squared plus a squared t dr divided by kc squared. Here 1 minus kc squared. K here is actually sin psi. Psi is actually here is 4 vector. 3 vector. Nu stands for it, and here is the time component. Actually, 3 vectors are called x to the I. I is 1, 2, 3, doesn't matter. This is just a magnitude of 3 components, 3D vector, and here is a time component. So if you express, if you write the whole vector, then we will use x to the nu. Nu is 0, 1, 2, 3. 0 is the time component. Time-like, space-like, or light-like trajectories. We will mention about them. It depends on the observations at some time. For example, if the events are space-like, or maybe let's imagine these events are time-like events, then two points in space can be described by the same time, but the space between them, the space components are not same. So the observations will agree on the invariant of time. They will measure d tau squared, same, minus the, dt squared, minus dt squared plus dx squared. Dx is 3 vector. So they will agree on time, but not the space. Or maybe d tau squared, tau is the proper time, is 0, which means that 2 events can be described as a light ray. So there is no difference. In ordinary Euclidean geometry, if the distance between 2 points in the space-time are 0, which corresponds that they are embedded each other. There is no distance. They are in the same place. But for the non-Euclidean geometry, non-Euclidean space, if the distance between 2 points are 0, which also corresponds that the events or the points can be described as they will participate or join like a light ray into the observers. If the events or points are space-like, then the space components are same, but the time components, you will never find the proper time that they can measure and agree on. This is special relativity and general relativity, actually, what we call it. We will explain laterly, but I am going to use this one. For example, xi vector and t. Here is 2 points in space, okay? So there's a distance in here. Doesn't matter what it is. Here are the components. If xi is dominated, let me call it. Proper time is actually that one. Let me call that. Let me take a look into the formulas. Here is a time separation between them. D tau is the proper time, is equals minus dt squared plus j. I think I have confused a little bit. Okay, this is plus. This is dxei squared, and actually from the triangle. Doesn't matter. We can write it like this. For example, if here must be minus. If here is dominated, then the events are like this. So as you can see, space are same maybe, or the times that they can agree on time, but not the space themselves. I have my own notes for it. I can read or share with you. All right. For example, here is the sign. Here is space-like and time-like will be something like that. So they will describe in time-like case that the space components can be same or in the same point. Spatial distance is less than the time, for example. If dt squared is dominant, so interval of those points between those points called time-like. They can be some places, and they can be same places. So if x, the space component, which is 3 vector, is dominant, then there is less time component in space. So the interval between those 2 points are space-like. And which means you cannot find any reference frame which the 2 points are at the same position. Just an explanation of this both of things. I just wanted to say, actually. All right, we are turning back. And by the way, I am using dxi divided by dt equals vi. And by the way, dx dt is the v. So what are those differences between the four velocity and the ordinary velocity? There are differences, but actually there's a relation between them. Okay, we knew, actually, we demonstrated as we knew. All right. So, for example, the zeroth component is actually the time difference. V0 equals d tau divided by dt. This is just a component, okay? And it can be written as different forms. For example, here, I can write it as dxi divided by d tau divided by, actually this is the dt divided by d tau. Here is actually the 4 velocity, vi. Here is the time ratios. If this dt and d tau is 1, there is no time separation. The ratio of the proper time and the ordinary time that is measured by the observers. All right, I will mention another time. Let's turn our points. I like this case most. Okay, here is that, okay. And actually recollect here was the Hubble constant squared minus 2gm divided by a cube t equals some constant 2a divided by mc squared of t. If I can write it as a volume, as we did in the previous video, m equals rho v, v is the volume, rho is the density. So 4 pi g divided by 3 rho can be written. But by the way, r, okay, I forgot. R becomes extended as the universe expands. So the material stretches out, which means that it also stretches out. And the distances are changing by a factor of a cube as a scale factor, recollect that. So if you can replace it into here, okay, if you replace it, and we assume that r is 1, it doesn't matter if it is different from the 1, r cube, a cube is here, and then it was also, they will vanish each other, cancel each other. So from instead of writing this, we prefer this. So you can write down as okay. Actually, there's a mistake, some mistake here. Rho m divided by v, rho v m. Okay. 3 rho divided by let's say 1 minute. Rho m divided by v. Rho v equals m. Oh, okay. We are just solve for a cube. Okay, for the volume. Then you get this one, h squared of t minus 8 pi g divided by 3 rho. How do you get? Do you understand? Here becomes this one, 3 rho v divided by 4 pi g. And if you divide, they will reverse each other, inverse each other. So it comes to the upper side as 8 pi g divided by 3 rho. And m's will be vanish, the bigger m's, and the great m's will vanish, equals 2a divided by ma squared. So h squared equals 8 pi g divided by 3 plus or minus 2a divided by ma squared. A is dependent into the k, the curvature of space. If k is positive, then a is negative. So the acceleration is determined by the sign of the a, which corresponds in here, for example, kc squared divided by a squared, which corresponds the sign of the k. Alright, in these videos we investigate the second order and the first order Friedmann equations so as to understand the expansion non-stationary case of gravitational field, that the radiuses are just increasing and growing up as the time passes. The next chapter we will solve this differential equations so as to understand the relation between the scale factor and the process, the time, and afterwards we will add curved spacetimes, which corresponds to geodesics. There are non-linear curvatures, which means that there are curvatures. That's all. If you have confused, just take a look into the previous videos. Also, the Turkish ones are also more clear, because in English it is harder for me still. Alright, for now it's okay. See you then.